can also define equality of two sets. It's a very simple idea. Two sets are equal. We might say set A is equal to set B if they have exactly the same elements. Otherwise, we say that A is not equal to B. So for instance here, the set containing the elements 1, 2, 3, and 7 is equal to the set containing 1, 7, 3, 2. Notice that the order is not the same, but for equality of sets it doesn't matter. What matters is there are exactly the same elements. There's a 1 in both, there's a 2 in both, there's a 3 in both, and there's a 7 in both, and there's nothing in one that's not in the other. That's all that's required for equality. Order doesn't matter. On the other hand, this set containing the elements A, B, and C is not equal to the set containing A, C, E because there's an A in both, there's a C in both, but there are elements in one that is not in the other. It only requires one case, but for instance there's a B here but no B over here, and here there's an E here but no E over here. So if there's any difference at all in the membership of the sets, then you would say the sets are not equal. Lots of definitions here, but you sort of absorb them by using them. I don't think it's so much a matter of memorizing them. We define something called a subset. We say that set A is a subset of set B if every element of A is also an element of B. And we write that using this notation, sort of a sideways U with a bar under it. That's read A is a subset of B. Okay, what does that mean? Let's do an example. If I have on the left the set containing A, B, and E, and on the right I have the set containing A, B, C, E, G, can I put the subset symbol between them? Well, here's the condition. If every element of A is the thing on the left, is also an element of B, which is the thing on the right. So I just start on the left and I look. There's an A here. If it's going to be a subset, there better be an A over here. There's a B here. If it's going to be a subset, there has to be a B on the right. Finally, there's an E here. If it's going to be a subset, there has to be an E on the right as well. So the idea of subset is like being contained within. So you're saying, are the elements of the set on the left contained within the elements of the set on the right? And the answer here is obviously yes. And you can see I did some color coding here so you can see that in fact they are contained. They're not equal because there are elements on the right that are on the left, but A is the set A, if you think of the one on the left as A, is a subset of the set B if you think of B as the set on the right. Because everything in the set on the left is contained within the set on the right. How about this one? Well, you look. If it's going to be a subset, whatever's on the left has to be on the right. Well, A is on the left, A is on the right. B is on the left, B is on the right. C is on the left, C is on the right. E is on the left, E is on the right. G is on the left, G is on the right. So yes, it is. Now you might say, but those two sets are equal. That's okay, they are equal, but that doesn't prevent the one on the left from being a subset of the one on the right. It just has to be contained. The elements on the left have to be contained within the set on the right. And they are. So that you could actually put an equal sign there and that would also be true. But the point is, in this context, it is a subset. That subset happens to be equal, but it is a subset. It doesn't matter that they're equal. In fact, and we'll talk about this a little more in detail, this little underline, this little bar, reflects the fact that they can be equal. It's almost like the less than versus less than and equal to when you're talking about the magnitude of numbers. How about this one? Well, start the same thing. You have dog on the left, you have dog on the right. You have cat on the left, but there's no cat on the right. Therefore, the set on the left is not a subset of the set on the right. Now, here's where you've got to put on your thinking cap and be careful. We just defined a subset. We're going to find now a particular kind of subset called a proper subset. A proper subset is a set, and the symbol is a sideways U without the underline, without the bar under it. Set A is a proper subset of set B if every element of A is also an element of B, but you don't have equality. So a proper subset and a subset, the strategy for deciding is exactly the same. The only difference is you cannot allow equality. If equality occurs, you can use subset, but not proper subset. So for example, going back to this same calculation before, you do it exactly the way you did for a subset. If there's an A on the left, there has to be an A on the right. If there's a B on the left, there has to be a B on the right. If there's a E on the left, there has to be an E on the right. So that is not only a subset, but a proper subset. It just can't allow equality. But here you don't have equality, so that's fine. How about this one? Well, you have an A on the left, an A on the right, a B on the left, a B on the right, a C on the left, a C on the right, an E on the left, an E on the right, a G on the left, a G on the right. So you say, okay, that's a subset. In fact, we just did it. It is a subset. But it's not a proper subset because a proper subset does not allow equality, and these two sets are equal. So even though those two sets are will fit the description of the left one being a subset of the one on the right, or actually even the other way around, they are not proper subsets because you have equality. You cannot have equality with a proper subset. That's the only difference. Otherwise, the analysis is exactly the same as for a subset. You know, just going back to the same ones. Dogs on the left, dogs on the right. Cats on the left, but there's no cat over here. So it's not a subset, nor is it a proper subset. So the analysis between set and subset are exactly the same, except you cannot allow equality for proper subsets. Now, I can't say this enough. If you're not careful, you're going to make some mistakes here. So you've got to pay close attention. I've tried to point that out, but you've got to be really careful between subset. Notice there's a little bar under it. That reminds you of the equality. They're okay to be equal, versus the one without the bar, which means it's not okay for it to be equal. And I mentioned this, I alluded to this a little bit earlier, but the last thing I'll say about this is sometimes analogies help you understand better. To me, there's an analogy between that and the idea of something being less than versus less than or equal to. Now, if that confuses you, don't worry about it, but it might help you understand the difference. Because if I put less than or equal to, it allows the possibility of equality. For example, 5 is less than or equal to 5. But if I don't put the equal to under there, and I just say 5 is less than 5, that's false. So for the same reason that it's okay if you put the symbol for a subset with the bar under it, you can have equality. But when you don't have the bar under it, that's proper subset, and it doesn't allow equality, so you have to say it's false. That analogy helps. Use it. If it doesn't, just go back to thinking it through directly. Now, speaking of subsets, there's a way to look at a set and decide how many possible subsets there are. And it's simply this. If you have a set with k elements, it has 2 to the power of k subsets. So for example, if I started out with the set ACF, which obviously has which obviously has 3 elements, then there will be 2 to the third, which is 8 subsets. Now, we can list them all, may not need to most of the time, but just to see that that's the case, let's actually list them all. Let's start off talking about the subsets that have no elements. There could be 1 element, there could be 2 elements, there could be 3. The whole set only has 3 elements, so those are the only possibilities. You could have a 0 element set, a 1 element set, a 2 element set, and a 3 element set. Those are the only possible subsets of a set that only has 3 elements in it. So let's start off with the no element subset. Well, that's easy. That's the empty set. The empty set is defined as be the set with no elements in it. The empty set is a subset of every set. How about the 1 element sets? Well, you could just take the set containing just A. You could take the set containing just C. You could take the set containing just F. So there are 3 1 element sets. Now let's do them in pairs. The 2 element sets, you could pair A with C. You could pair A with F, or you could compare C with F. Now remember, order doesn't matter, so you're not going to list FA and FC and CA as different subsets. So there are also 3 2 element sets. Now obviously there's only one 3 element subset, and that's the set itself. And if you count them, that's 1, 2, 3, 4, 5, 6, 7, 8, just as we predicted. So that formula will tell you how many subsets a set has. So we know how to count the number of subsets, but what if we're interested in the number of proper subsets? Remember, for a proper subset, you can't include the set itself. So if you're asked about subsets, it's 2 to the k for a set with k elements. But if you're asked about proper subsets, you cannot count the set itself, so it goes down by 1. So it'd be 2 to the power of k minus 1, which would be only 7 for a set with 3 elements. So if k is equal to 3, for the problem we're looking at, there would be only 7. In general, it's 2 to the power of k, and then take 1 away. It's just 1 less than the number of subsets. If you had a 4 set, it'd be 2 to the 4th for subsets, that'd be 16, but it would be 1 less than that, 15, for the number of proper subsets. So you just take the number of subsets and take 1 away if you're talking about proper subsets. We also have the idea of equivalence of 2 sets. It's different from being equal. 2 sets are said to be equivalent if the 2 sets have the same number of elements. That is, the number of elements in A is equal to the number of elements in B. Equality requires that the elements be exactly the same. Equivalence only requires that they have the same number of elements. So be careful about that. I think maybe the best way to think about the equivalence of 2 sets is just think of the elements as names or labels, and I like to use an old analog clock analogy. Some analog clocks just have ordinary Arabic numerals 1 through 12 as labels, but some have Roman numerals as labels. But they mean the same thing. Whether I use the Arabic number 1 or the Roman numeral 1 or the Arabic number 6 or the Roman numeral 6, none of that matters. It's just that they're the same number. They're going to be 12 of the labels no matter what you use for them. That's the sense of equivalence. In that sense, we would say a set A containing the Arabic numerals 1 through 12 is equivalent to the set B containing the Roman numerals 1 through 12. And in that same sense, even though it might look ridiculous, I would say the set containing A, 2, 5, and F is equivalent to the set containing dog, cat, bird, and pig, simply because there are 4 elements in each. By contrast, I would say the set containing the elements P, Q, and X, that set is not equivalent to the set containing A, 2, 5, and F because there are only 3 elements in the first set and 4 in the second.